Okay, Algebra 2 students, let's review in behavior. So, identifying if you're an even or odd degree and leading coefficient. So this one starts down, ends down. Even degree, positive leading coefficient. Starts up, ends up. Positive leading coefficient, even degree. Starts up, ends up. Odd degree, positive leading coefficient. Starts down, ends up. Odd degree, negative leading coefficient, starts up, ends down. And odd degree, negative leading coefficient, starts up, ends down. So you should be able to write that mathematically. Remember, start is x goes towards negative infinity. End would be x goes to positive infinity. Up is f of x goes towards positive infinity. And down is f of x goes towards negative infinity. So looking at this example, it starts down. So it would be one of these and then one of those. And then it ends down. So it would be one of those and one of those. Looking at this one, it would be start, so it's here, starts down, so start one of these, and then ends one of those. So this is the math way of writing it. This is the kind of colloquial way of describing it. Starts down, ends down. Good? Now I want to show you some things on DESMOS. So let's take a look here at the next slide. So I'm going to go over to DESMOS, and I'm going to graph some things. So first thing I'm going to graph is y equals x, which you may not think of as a polynomial, but it is. Now I'm going to graph it as x minus 0. Good? And then I'm going to change that 0 to a 1. And then I'm going to change that 1 to a 5. And then I'm going to change that 5 to a negative 3. And hopefully what you're seeing is this x-intercept is changing for each one of those values. So I'm going to use a little slider here called A. Look what happens as I move that A value. Notice that the x-intercept is that x minus A. Good? Now I'm going to change the power here, and I'm going to raise this to the second power. And now look, it's still the same 0, but look what happens. It bounces as it goes off. I'm going to change it to a 3. Now look what happens. It's still a 0, but it passes through the x-axis after it flattens out. I'll change this to a 4. And look at that. It bounces up, and I'll change it to a 5, and a 6, and a 7, and an 8, and a 9, and a 10. And some of you saw this one when I did 43, or I did 34. So what that number is, that number, that exponent, is actually what we like to call in math, and I'll just write this on here, it's called multiplicity. That number right there is the multiplicity. Multiplicity of a 0. Now a 0 is a value of x that just makes the function 0. In this case, x equals 1 is a 0 of this polynomial, because right now it's y equals x minus 1 quantity cubed. That 1, it's minus 1 because that's what a is, that 1 is the 0, and the 0 has a multiplicity of 3. When a polynomial has an odd multiplicity, it will pass through the x-axis. But based on the number, it will flatten out more and more. So if I've got to erase all this to change the numbers, if I change that number, to a 1. Do you see that it does cross the x-axis at 1 and it passes through? If I change it back to a 3, do you see that it flattens out before it passes through? If I change it to a 5, it just flattens out more, or 7, or 9, or 11, or 13, or 15. Every single time it's passing through the x-axis, but it's flattening out before it crosses. Now, you might be saying, well, it looks like it's at the x-axis a lot. It's not. It's just we got to zoom in and see. It's just getting so close to the x-axis that our scale can't really show the difference, right? So it's hard to get to that point where you can see how much it actually is getting closer and closer to 1 without ever hitting there. Right? The values of y are so small because the difference in here is so close to 0, and if you raise that small difference to the 15th power, it just gets really small. Right? Look, you can see how close. Those are all x values. The y value is practically 0 there, according to DESMOS. Right there at 0.475, you can see that the difference is negative 1/10,000th. So that's pretty small, right? So knowing that an odd multiplicity flattens out and then passes through, and that an even multiplicity bounces. So 2, 4, 6, 8, 10, 12, 14. So what we're seeing here is depending on the number of times that factor is repeated, we know what's going to happen at the x-axis. It's going to either bounce from the direction it came or it will pass through if it's odd. So if we put those two ideas together, that x minus a gives you an x-intercept of a. That's also called a 0. It's also called a root. There's 3 names for it because it's pretty important. And that the power up here, b, is called the multiplicity. Multiplicity. And if it's even or odd, so odd, it passes through. So it either goes from top down, or it goes from bottom up, or even if it's coming from the upside, it turns up, or if it comes from the downside, it turns down, right? So that's convenient. So putting those together, we can actually graph most polynomials if we can get it into what's called intercept form. And we can make note of their multiplicities. So take a look at this example. It's easy to see here that the multiplicity of each of these zeros is 1. So x equals 1, x equals 3, and x equals negative 2. Good? So I can go ahead and graph those x-intercepts. X equals 1, x equals 3, and x equals negative 2. The other thing I can see here is if I just multiplied the first terms out, I would get negative x cubed. So that's negative 1 times x times x times x. And if I just multiply the last numbers out, I would get negative 1 times negative 3, which is 3, times 2, which is 6, times negative 1, which is negative 6. That's your y-intercept. Now, the other thing I can see is it's a negative leading coefficient, so it starts up and it ends down. And now I can basically graph this polynomial from what I know. It's going to fly right through this 0. Why? Because that has a multiplicity of 1, and so it has to pass right through. Then it's got to hit this y-intercept, and then it's got to turn up. Good? Then it's going to fly right through this 0. And then it's going to turn down for what? Turn down for what? Turn down to hit that 0. And now we're done. Now, that's not a great graph, but it's a pretty good sketch. Here's X, here's Y. And if we go look at DESMOS, let me clear all that writing. Let me put in the -1 here. And you can see all those things I got. -6, I've got the 1, the 3, and the 2. Now, I just erased my graph, but I think it looks something like this. So I'm going to graph it here. Sorry, hold on. Let me clear all this. All right. So I think I had a graph that looked like this. Okay. Now, it's not exactly this, because if you notice, there is a minimum here and a maximum here. The only way you can know that the maximum or the minimum is down here and the maximum is right there where it is you got to take calculus. Without doing calculus, I can't find that point without a calculator. But it doesn't matter how rough my sketch is, because it's just a sketch. It's just an idea. Now, while I have this DESMOS up, look what happens when I change the power here to an even power. Now, you should think about what happens if I square this before I hit the 2. Now, look what happens. It is a negative leading coefficient, right? -1. It's an even degree now because I'm squaring this. 1 times -1 times -3 is 3. 3 times 4 is 12. 12 times -1 is -12. Do you see the y-intercept of -12 there? Notice that it has to start down and end down. And now why would it hit this 0 and turn down? Because that 0 happens twice. So why does it turn down? Turns down because of the even multiplicity. And the other ones, it just passes through. Now watch what happens if I change this one to an odd degree. Do you see how it flattens out a little bit? Now I'm going to go ahead and get rid of this back to a 1. Good. Do you see right there at that 0 now it's flattening out? Now it doesn't flatten out a ton, but it's more flat than if it was just a 1. Do you see if it's a 1 it just flies right through, but if it's a 3 it flattens out. If it was a 5 it would flatten out even more. If it was a 9 it would flatten out a ton. Good? If I make that a 3, it doesn't change the overall degree from being odd. So notice it still starts up and ends down. If I make this a 3, now it's still an odd, and you can see that flattening out there. Good? If I make this a 2, well, now it's an even degree. Do you see how little that bounce is? It's kind of hard to see, but it does bounce off there. You see that? And you have to zoom in a lot to see how much it's actually, to see that kind of curved bounce, right? And if I change it to a 4, it's going to flatten out so much now. I'll have to zoom back out, and now you can see how much it flattened out, right? And if I change it to a 40, well, that would just be ridiculous, right? How much it flattens out. Now, these things look like they're straight up and down, but we know they're not. We know they're not because it wouldn't be a function if they were straight up and down. But basically, I should be able to give you any polynomial in factored form, and you should be able to sketch the graph. We're not going to do anything too crazy, but getting to this factored form is a skill I can teach you. We're not ready for it yet. Right now, we're just going to be graphing polynomials in factored form. All right. Peace.